series on differential geometry. In this section, we talk about curves in R3. We define a curve in R3 to be a differentiable function alpha from an open interval I into the set R3. For a simple example, we can consider the curve alpha of t defined as the set of points p plus tq, where p and q are points in R3, and t is a real number. This curve is exactly the form of a straight line. P is the point alpha of 0, then p plus q is a point alpha of 1. All other points on the curve are in the direction of the line which contains p and p plus q. For a more complicated example, we can consider the curve alpha of t defined as 1 plus cosine of t, sine of t, and 2 sine of t over 2, which is the curve that lies on the intersection of the sphere of radius 2 and the cylinder extending perpendicular to the xy plane with center the line z0, 0, which is the line which is parallel to the z-axis and intersects the xy plane at the point 1, 0, 0, and the cylinder is of radius 1. In the figure, we have an outline of the sphere and that cylinder, and it intersects the sphere along the red curve. We will say that a curve alpha of t is differentiable if each of the component functions alpha I of t are differentiable. Then we define the velocity vector of alpha as follows. Let alpha be a curve in R3, and write the components of alpha as alpha 1, 2, and 3. For each number t in the interval I, we will call the velocity vector of alpha at t the tangent vector alpha prime of t, where the point of application is alpha of t, and the coordinates of the vector part are the derivatives of the components of alpha evaluated at t. Next, we define the reparametrization of a curve alpha as follows. Let alpha be a curve if h is a differentiable function from an open interval j to the interval I on which alpha is defined, then the composite function beta, which is alpha composed with h, is a curve from the open interval j to R3, and we call this the reparametrization of alpha by h. Now we prove a few simple lemmas. Firstly, we prove that if beta is a reparametrization of alpha by h, then the tangent vector beta prime of s is just the tangent vector of the composition alpha and alpha composed with h, but then multiplied by the factor dh ds, the derivative of the inside function. So hopefully that we can see that this is essentially just the chain rule, but for tangent vectors. To prove this, we'll write beta of s, which is alpha of h of s, in coordinates. Each of the components are alpha I of h of s. we use a definition of the velocity vector and just the traditional chain rule to obtain beta prime of s. We replace each of the coordinates with the derivatives of the components. Since each of these components are just functions from r to r, we can use a chain rule on each of them so that the derivative of alpha I of h of s becomes alpha I prime of h of s times the inside function's derivative h prime of s. Since each component shares a factor of h prime of s, we can pull that out front. Then we can rewrite h prime of s as dh ds. And of course, the vector alpha 1 prime of h of s, alpha 2 prime of h of s, alpha 3 prime of h of s is just the tangent vector of alpha prime at h of s. Next, we consider the lemma 4.6, which states, if alpha is a curve in R3 and f is a differentiable function on R3, then the directional derivative of f in the direction of alpha prime of t is written the derivative of f of alpha dt with respect to t. Next, we consider this lemma, letting alpha be a curve in R3 and f a differentiable function on R3. Then we can write the directional derivative of f in the direction of the vector alpha prime of t as df alpha dt of t. This is only for notational convenience in the future. Before proving this, we'll just remark that we can use lemma 3.2 immediately for this proof. Lemma 3.2 states, given a tangent vector v applied to the point P, the directional derivative of f in the direction of Vp can be written as this sum, which has the appearance of the chain rule. Okay, we'll use lemma 3.2 in just a second. Now let's prove lemma 4.6. We'll write the velocity vector alpha prime in components, with each component the derivative of alpha I with respect to t. And now we apply lemma 3.2 to obtain this formula for the directional derivative. So here, instead of the vi's, we have the components of the velocity vector. Those are the d alpha i's dt's. These are functions of t. Then we have the partial derivatives of f, which are part of the formula seen in lemma 3.2. Similarly, we find that the derivative of f of alpha of t, which is the derivative of the vector with components f of alpha I of t, obeys the chain rule since each of the components are functions of one variable. So we can simply use the chain rule and obtain the exact same formula as above. This gives us some assistance with computing velocity vectors and directional derivatives along curves for the future. And that's the main takeaway of this section.
Thank you.